data. Data is filled with variables. It could be a qualitative or a quantitative that varies between samples. And what is data other than the variables? It's information that gathered about the variables, and we need to reach to a conclusion after gathering variables. For example, like cotton is a raw material for clothes. Data creates study results. So the interpretation of proper data is required for understanding the studies. So if you want to classify data, we can divide it into, once we collect all the data, we can divide it into two sections majorly: qualitative and quantitative. So the qualitative, well, I'll give you examples later in the lecture. So qualitative and quantitative was one thing. Then we can subdivide it into continuous, discrete, nominal, and ordinal data types. So in quantitative data types, we answer how much, measurable as numbers, like height is measured in centimeters, weight in kilos, BP in millimeters of mercury. And whereas qualitative data, we answer what type. It describes character or quality. It's like hair color, blood groups, gender. We don't have any quantity in this one, right? So it's a type. It's a qualitative data. So in quantitative data can be divided into, again, a continuous data where there is no gaps between measurements, like serum cholesterol. Like we have, in during our testing blood investigations, we can have it as 188, 188.1, 188.12. So this is a continuous data and there are no gaps between the measurements. And there can be some measurements such as known as whole integers, and that is discrete data. You can't have something in between these things. There can't be any decimal numbers. So that those are called as discrete data, such as number of malaria. We don't have any 2.3 malaria cases, right? It is a discrete quantity. And continuous data can be measured on a scale and can take any value within the range. Example includes, blood pressure measurement. It could be 120 by 80 or 121 by 82 as well. Height measurements 121, 172.5, 185.3, like that. And similarly, weight and also lab values. So these measurements can be divided infinitely and maintain meaningful values between points. Okay, so we have these various data. Whereas discrete data examples like malaria cases, whole number of infected individuals, the number of deaths or fatalities from myocardial infarction. So this is a discrete data example. And if you want to quantify adverse reactions, we count the number of, count the medication side effects. Qualitative data types are subdivided into nominal and ordinal. So nominal data are named categories. That is, there is no relationship or hierarchy in this. It's just a like a color or something like that. Okay, so there are, you can't distinguish between those two. Like nothing is superior or inferior. It's just the types. That's called as nominal. Whereas ordinal data, these are category with specific order. It shows a sequence only, right? So it includes examples such as pain, mild, moderate, severe pain, and fever, low grade, high grade fever. So these are ordinal data. Nominal data, from it is derived from the Latin nomen, meaning name. It's a simple naming system. Item shares something in common, and there is no hierarchy. Categories have no inherent order, and independent categories. No category is superior to others, as we have mentioned. So nominal data examples include eye color, black, gray, blue, brown; gender, which is male, female, or other; blood groups A, B, O, ABO, something like that. Okay. And ordinal, you have a specific order. Categories follow a logical sequence. It shows ranking. Position on the scale indicates order. And no arithmetic. Cannot perform calculations with the values in this data. Ordinal data example includes pain intensity, mild, moderate, severe, blood pressure, whether it is hypotensive, normal, high normal, grade 1 and grade 2. Disease staging also comes under ordinal data: stage 1, stage 2, stage 3, stage 4. And other than these, we have something called as binary data, where we can define the data into only two things: whether yes or no, plus or minus, like that. Okay, so variable with only two possible values, and there are no alternative. Only two mutually exclusive options are applicable in this. Examples include like yes or no, dead or alive, present or absent. We can't have in between and also alternative other than this, right? So this is binary data. So the binary data classification can be done in terms of binary nominal, like male, female, smoker or non-smoker, without any order. Binary ordinal, where two categories with implied order, like pass or fail. Pass is somewhat better than fail, right? So obviously it is it's implied. And responder versus non-responder. Responder, like if we in a hypertensive patient, if we give fluid, the patient will responding. It's called he's those patients are called as responders, and who are transiently responding, those are called as transient responders, and those who are not responding, they're called as non-responders. It's a binary ordinal, again with implied order. And to summarize, so we have quantitative, qualitative. Quantitative continuous will be serum cholesterol, HbA1c, BMI. Quantitative discrete, discrete will be number of malaria cases, deaths, and adverse events. Qualitative nominal, eye color, gender, blood groups, religion. And qualitative ordinal will be headache, severity, blood pressure, status, and etc. So if you want to convert a quantitative to qualitative, we need to start with numbers. Quantitative measurements such as 181 or 134. Then we will define cutoffs. We predefine category boundaries. Then after that, we'll create categories. We'll assign qualitative labels such as short, average, tall. So this will convert a quantitative variable to qualitative. When we convert, such as example, blood pressure, so you will measure the blood pressure. Quantitative is 120, 140, 190 millimeters of mercury. Then you will apply categories, whether which is normal, which is borderline, which is hypertensive. Then you will report proportions, percentage in each group. Then when you're converting, you need to be, and you can just categorize. So if it is 190 by 110, it is hypertensive, right? So you will categorize it accordingly, and you will report percentages in each group rather than that. So when we are converting a data, that we need to also remember some caution. We should be cautious because it will weaken the data. So converting a quantitative to qualitative loses precision. And there is also clinical differences in this one as well. So if BP of 150 versus 210 have different outcomes, obviously, and only convert when it is necessary. You should use it very sparingly as well. So for example, quantitative, patient A has 150, patient B has 210, difference is 60, and different clinical implication. Qualitative, patient A is hypertensive, patient B is also hypertensive, both above 140 millimeters of mercury cutoff, significant difference lost, right? So based on this example, you can see even though the patient B has very high 210, it's a significantly high when compared to 150. So there is clinical difference of 60. It's lost when we convert it, right? Because we are labeling both the patients as hypertensive. So the significant difference is lost when we convert it. And why data types matter? It is required so that data collection is done properly. It determines measurement approaches. And statistical analysis, it determines appropriate tests, what and which type of test we need to do. And also data presentation. So once you collect, then you analyze, you need to present it so that the effective outcome can be measured, right? And so data presentation, it helps in that one as well. And finally, interpretations. It affects conclusions drawn the way after the way you present the data properly. So the data types matter a lot. So collection, analysis, presentation, and interpretation. So these are the important steps in data types, if why it matters. Okay. And how do we define, and also how do we know which type of statistical test to select? So we have different tests, and which are named after various other some scientists, and also some based on the formula and other things. So qualitative data always analyzed by non-parametric tests, such as chi-square, Fisher's exact tests, McNemar's tests, whereas quantitative use parametric tests if normally distributed. And the various tests used are t-test, ANOVA, Pearson's correlation. So normal distribution a requirement. So bell curve pattern data must follow normal distribution for parametric tests to be applicable on them. And we need to test normality, and which we use Shapiro or Kolmogorov Smirnov's test. And if there is non-normal data, then we have to use non-parametric alternatives if distribution is skewed. So parametric versus non-parametric. So parametric tests are such as independent t-test, paired t-test, one-way ANOVA, repeated measures ANOVA, Pearson's correlation. Whereas non-parametric equivalents include Mann-Whitney U-test, Wilcoxon's signed rank test, Kruskal-Wallis test, Friedman's test, Spearman's rank correlation. So the various parametric and non-parametric tests are used accordingly based on the data types which we extract. So categorical data again. So once we this is about the test, right? So now we'll come to the visualization part. How do we visualize data? Categorical data are visualized with bar charts, pie charts, and frequency tables, whereas continuous data are measured and also visualized in histograms, box plots, scatter plots. And whereas time series are you know plotted or visualized with line graphs and area charts. So, and data can be distributed anywhere, so we need to find some other during when we collect the data, we have some other variables to discuss. So there is something called as central tendency, which is measured with mean, median, and mode. And there is something called as dispersion. So we have the center, then we have the periphery, that is the dispersion. The dispersion is measured with range, standard deviation, interquartile range. And after this, so we will overall assess the distribution, whether the distribution was is of normal or if it is skewed. And we'll also check for the kurtosis as well. So qualitative data again usually will have a frequencies counts in each number. We do percentages in each category, that is called as proportions, and we'll compare between the categories, that is called as ratios. So I'll just summarize this. So we have quantitative data, two things: central tendency and dispersion, and then finally distribution overall. Then whereas qualitative data, frequencies, proportion, and ratios, these are the three things that are important. So when we are planning data collection, we will define the protocol. If we specify data types beforehand, right? And also we measure and also select appropriate instruments to measure. So we select our measurement tools as well. Then the collection methods, we standardize the procedures, the way we collect the measurement tools and other things. So when we are collecting data, the data quality considerations include usually accuracy, the correctness of the measurements, whatever we measure, whether we are doing it correctly or not, and the reproducibility of the measurements, precision, how precise it is to the measurements. Okay. Then completeness, whether there are any missing values or not, and consistency, uniform collection methods. So these are the various things which we do. And when we handle when we have any missing data or values, then we have to identify, we have to detect it accordingly. Then after that we have to analyze whether it is random or systematic, and we have to choose the method to either manipulate it or delete it. So most times deletion will be imputation, sorry. Deletion or imputation usually will be done. No manipulation, sorry for that. And after collection, we do what is called as data cleaning process. First of all, we check for errors. We identify outliers, and we also look for inconsistencies and duplicates. We remove it, like deletion or imputation. Then we validate the values. We ensure that measurements within the plausible ranges or not. Then we standardize the format, that consistent units will be done and coding and categorization will be done. Then we document the changes. We record all modifications to our raw data. So this is called as data cleaning. So we errors is first thing, then we validate, then we standardize, then we document the changes. So the common data collection errors include measurement errors. So incorrect, inaccurate instrument or techniques causes measurement error. And there can be recording errors because of mistakes in data entry or transcription. There can be sampling errors where non-representative selection of subjects, when we consider them, then that is called a sampling error. And processing error will be mistakes during the data transformation. So these are the various errors that can happen during our data collection process. So in data in clinical trials, usually we have a data, but beforehand we will, have a protocols which defines the variables and endpoints. Then we gather in measurements per protocol, that is called as data collection. Then we monitor the data to ensure quality and compliance. And finally, when we get the data, we analyze it appropriately and dividing them into qualitative or quantitative. And so then after that, we analyze it, appropriate statistical methods, applying them. So we can also divide the data into primary data and secondary data. So primary data is the one collected firsthand for specific research, such as direct measurements, surveys, interviews. So this is directly firsthand for specific research. This is called as primary data. Then when we survey the existing data, which is repurposed for new analysis, such as when we consider some medical records, published studies, databases. So this is called as secondary data. So we can have primary or secondary data. And the data collection methods will include, usually one thing is direct patient assessment. So this is called as clinical examination. And so by direct patient and assessment, and we record the findings. So this is one type of method to collect data. The other type will be based on the laboratory tests, biological sample analysis. Then sometimes if the patient is conscious and also well educated, usually, so then we can have a questionnaire. This is self-reported information. And other than that, records review. So existing documentation analysis can also be done in these patients, in these to collect the data. So clinical examination, laboratory tests, questionnaires, and records review. So these are something which methods for data collection. And sample size consideration also is important when we are doing, because we can't calculate and also measure entire population. That will be time consuming, resource rich, and also manpower and other things will be taken should be taken into consideration. So that's why we only study a random sample that is representative of the entire population, and then we extrapolate. That is how we have test our hypothesis in research, right? So for which sample size is important. Sample size, when we considering that, it depends on the research question. So we have to define a primary outcome measure. Then based on this, we can alter our sample size. And also the effect size to determine the clinically meaningful difference. So the effect size is important for also for the sample size considering. And also statistical power. We need to set desired probability of detecting effects of that of these the of our study, and we will calculate it accordingly. So we will use appropriate formula based on data types to select it. And once we do that, we have a data type impact on our this one. So we use sample size consideration, whether continuous data based on mean difference and standard deviation. Binary data based on proportion difference. Ordinal often requires larger samples than continuous. Nominal data depends on number of categories and distribution. So the various data types have different impacts on the sample size. So it depends on the categories, distribution, and other things, and larger samples and proportion, etc. So once we get the sample, then data, then we have to store it, right? So we have something called as data storage, where we have a database design where we have structured storage system, and we have protection, security, protection from unauthorized access. Then we back up that regular duplication to prevent loss. Then we have access control permission based on roles into that data. And once we secure our data on cloud and other things, so data privacy consideration should also be done. De-identification, consent, regulation, and access limitations should be checked properly before, for the proper data privacy. And once we do that, so we have raw data, right? Raw data, those are original character values. We clean, normalize, aggregate, then we make it analysis ready. So we prepare for statistical testing. So common transformations include logarithmic, where for skewed data, to achieve normality, we square root it for count data with zeros, and or else we will inverse it for severe right skew, and we standardize, convert to z scores for comparison. So these are common transformations during our data cleaning process, and where we standardize our data: logarithmic, square root, inverse, standardization. Once we done that, then we have collected, we have stored, we have analyzed, then we interpret, right? So interpretation, there are some challenges with it. So there can be some bias recognition. So we need to identify the systematic errors in our data. We have to contextualize our understanding of the data. We have to consider the clinical relevance beyond the p-values. We need to acknowledge limitations. We need to recognize constraints of our data and methods. So beyond p less than 0.05, there are three types of lies, commonly said, in a funny way. Lies, damn lies, and statistics by Benjamin Disraeli. So effect size is important. Magnitude of difference matters, not just significance. And confidence intervals, range of plausible values, not just point estimates. Clinical relevance, statistical significance is not equals to, it does not equal to clinical importance. So we need to understand that effect size, confidence intervals, and clinical relevance. So these parameters should be taken into consideration when we are interpreting our data, because there can be some studies where p-value will be less than that, but the effect size, confidence interval, and also clinical relevance may not be that significant. So we need to consider that when we are interpreting the data. So data in evidence-based medicine will include, clinical decision, informed treatment choice, evidence integration, combining research with experience, critical appraisal, evaluating quality of evidence, and research data, foundation of evidence. So these are the various things. So one thing is foundation of evidence, then critical appraisal, the evaluating quality, then evidence integration, combining research with experience, and informed treatment choice. We have different levels of evidence based on the studies. So systematic reviews, meta-analysis of multiple studies, where we have already published studies will be analyzed by qualified researcher, and after that the evidence will be put forth, and this is the highest level of evidence. And we have something called as randomized control trials, which are experimental studies with randomization. And if it is multinational, multicentric, and double blind or triple blinded randomized control trials, that will yield high level of evidence. And we have something called as cohort studies, where a particular cohort will be studied over time based on the risk factors and exposures, and this is somewhat less when compared to the randomized control trial and systematic reviews and meta-analysis. Case reports are individual patient descriptions here and there. These are usually good for some rare cases, and usually this is of lowest evidence level of evidence. And the best practices of data visualization include simplicity, accuracy, clarity, and relevance. So based on this, we need to visualize our data properly, and we need to be transparent integrity should be maintained. We should need to responsibly, handle the sensitive information. We need to be accountable, taking ownership of the data quality. And we need to avoid statistical pitfalls like p-hacking, analyzing multiple outcomes until we find significance, which is called as p-hacking, and cherry picking, selectively reporting favorable results, and that is not good for the research outcome, right? Hawking, and this is hypothesizing after results are known, so this is called as harking. And overinterpretation, drawing conclusions beyond what data supports. So this, we need to avoid these pitfalls, okay? and and after that, we need to look for detail, reproducibility in research as well, detailed methods, comprehensive documentation of procedures, and analysis code, sharing scripts used for data processing. And we need to access we need to have access to raw or processed data sets. So the data availability should be there, and pre-registration, declaring hypothesis before collecting data, so that we can properly analyze and also assess our hypothesis, right? So based on this, we need to do that. Okay, so, and in, there are some challenges in healthcare where, when we have big data. So the sources will be electronic health records, wearable devices, genomic data, insurance claims. The challenges will include volume management, data integration, privacy concerns, quality assurance. And there are a lot of opportunities in predictive analytics, personalized medicine, population health, and resource optimization. And we have something called as machine learning and data, where machine learns about the data, it collects, processes, pre-process, model is trained, and validation is done. And we have, machine language, models, and which has, some model performance, accuracy, precision, recall. Then feature engineering is one thing which creates meaningful variables. Then after that, data pre-processing is done, where cleaning, normalization, encoding is done, and data quality is measured. Then the future will be of real-time monitoring, precision medicine, and AI integration. So the data literacy for clinician is important. So basic understanding, we need to recognize the data types, appropriately evaluate. The critical evaluation is that should be done of the validity of the research methods and conclusion. We need to apply it for the practical purpose. Otherwise, the what is the point of, learning about the evidence-based medicine if you're not applying properly, right? So that's why it's important to have a practical application. And after that, continuous learning, because you need to be a student to always learn about the various advances all over the world, right? The key takeaways are of this presentation are the different data types, the classifications, the tests which we use. Okay, quantitative data, we need to understand that it can be continuous or discrete. Qualitative can be nominal or ordinal. And the analysis section selection, that is the data type determines appropriate statistical tests. And the study planning, so most important thing is we need to define our data types before collection begins. Thank you for paying attention. It really means a lot. If you have any questions, post down below in the comment section. Thank you very much. Thanks a lot.